Hey everybody, we are live with yet another live office hours session with Chegg. As a reminder, this is the fourth session. We are going to be doing these all semester long. We are doing live office hours for Organic Chemistry 1. And so I have questions prepared. I'm trying to roughly follow a typical OChem 1 syllabus, but I am also accepting questions from anybody in the chat. If you'll notice my voice, I am still a little bit sick, if you can believe it. Last week I was rather sick. I'm a lot better, but I am still a little bit sick. It's been a really rough winter, but I'm going to power through it here. I'm going to answer all of your OChem questions. As a reminder, on the top left, there is that QR code. If you want to go over to Chegg's website or Chegg's YouTube channel, there is a list of all the various office hours that are being offered. So in addition to Organic Chemistry 1, you may find some very valuable help with other subjects that you may be taking this semester. But other than that, yes, once again, we are doing Organic Chemistry 1 with me every Tuesday at 5 p.m. Pacific, and we will be doing that all semester. So without further delay, let's go ahead and get into some of these questions that I've prepared. So if you recall, last week we started getting into the SN1, SN2, E1, E2 mechanisms, because that is really the first very major hurdle that I think a lot of students have trouble with in OChem 1. But so we're going to go over some of the basics there. And then I added some addition reactions towards the end, as I did say that we would start to get into those. And then next week we'll focus quite a bit on the addition reaction. And start with this first one here. Conditions that can achieve the following transformation. So we have this hexane, we have this substituted hexane. And what do we have on here? We've got a chloro group right there. And then we've got SCH3 right there. So how are we going to achieve this? At first glance, it seems like we might be able to do like an SN2, right? We can do some substitution, but pay attention to the stereochemistry. This chloro group is on a dash bond. This group is also on a dash bond. And we know that SN2 involves inversion of stereochemistry. Here we can see that the stereochemistry has been retained. So let's think a little bit about what we can do. If SN2 inverts the stereochemistry, then doing another SN2 reaction will bring the stereochemistry back to the original. So what if we were to do two SN2 reactions in succession? So we invert the stereochemistry and then invert it back. So let's do this. Let's say we do something like, and this could be anything. This could be really any SN2 reaction. Let's say we get the bromide, right? The bromide ion will go ahead and attack here, kick off the chloro group. And now we have inversion of stereochemistry, and we have the bromo group there, right? So this is an SN2 reaction. And now we are ready to do yet another SN2 reaction to get to our product. Now we need SCH3 on there. So let's get an ionic compound with this as the anion. So how about NaSCH3? We just need one of our metal counter ions. Could be sodium, could be potassium. Has to have a +1 charge, right? Because SCH3 has a -1 charge. So SCH3 minus will also go ahead and do the exact same thing. SN2, backside attack, the backside attack, again, because it has to access the lowest unoccupied molecular orbital, which happens to be 180 degrees away from that carbon-bromine bond. It's going to do a directly backside attack. And so that will be another SN2, and that will get us to our product. So with these reactions, stereochemistry is very important. Some reactions are stereospecific. SN2 is a stereospecific reaction. You are going to get an isomerically pure product. If you have a chiral starting material, as we do, you're going to get a chiral product, and it will be only a particular stereoisomer. In this case, enantiomer, because we only have one chiral center. So we did one SN2 to get the bromo group on there, and then another SN2 to get the new desired substituent. And that one is a pretty easy one. Okay, let me take a look at the questions. Okay, so Freak Guy asks about conformational analysis. We were talking about this last week and the week before. Why are anti-conformations more stable than gauche conformations, like in the case of 1,2-dihaloethane, sigma BMO and AMO? So it doesn't really have to do with orbitals, to my knowledge. It's simply that when you have a gauche configuration, those groups that are producing steric hindrance are closer together than 180, right? Anti is 180. That's the farthest away they can be. Here we have a 60-degree dihedral angle. They're closer, and so there's going to be some steric repulsion there. They're just not as far away as they could be physically, right? It's the same as with Vesper geometry. If you have something that's tetrahedral or trigonal bipyramidal or whatever it is, those bond angles are dictated by those groups getting as far away from each other as possible in three-dimensional space. So that's really all it is. Okay, let's go to the next one. R2-bromobutane will produce what compound under the following conditions? So we have three different sets of conditions. We have three different mechanisms that are going to occur. So let's see what happens. We've got R2-bromobutane. That's this. So it's 2-bromobutane, and this is R because this, remember, under the Con-Ingold Prelog convention, the bromo group would be priority 1. This carbon leading towards the ethyl would be priority 2. The methyl carbon would be priority 3, and the implied hydrogen would be priority 4. So this would go clockwise R. So that's R2-bromobutane. That will be the starting material for all three of these questions. And so now we have potassium hydroxide, and it's hot, 100 degrees Celsius. So what are we going to get? Well, okay, so with all of these, SN1, SN2, E1, E2, we're going to look at a few different things. We got to look at the strength of the nucleophile or base. We got to look at leaving group ability. We got to look at degree of substitution on the substrate, and we got to look at temperature. Those are the four factors that you're going to look at when you want to determine what mechanism is going to take place. And I'll give you a hint. The first thing we're going to look at is the strength of the base, right? So we have potassium hydroxide. Now, the first thing we must understand is that KOH is not a covalent compound. It's K plus and OH minus, right? And the metal counter ion doesn't matter. It's just there, right? Potassium hydroxide is a source of hydroxide. We write potassium hydroxide because ionic compounds, right? We can't go in the lab and get go to the jar of hydroxide ions and get hydroxide ions. It's got a negative charge, so it comes in ionic compounds that are where it's paired with a counter ion. So we can get potassium hydroxide, we can get sodium hydroxide pellets. It's an ionic compound, but it's not always explicitly stated that these are ions. So you have to know, right? You have to know that we've got a hydroxide ion and a potassium cation. So the hydroxide ion is very strong. It's a strong nucleophile. It's a strong base, which means we are not going to have to wait for a carbocation to occur. Okay, so SN1 and E1 are not going to occur. We have something that's very strong. It's going to push the substrate around. It's going to react. It's going to do something, right? It might coordinate. It might do elimination, grab a proton, whatever it is. So from that, we know that SN1 and E1 we're not going to go that way. We're going to go either SN2 or E2. Now let's look at the degree of substitution on the substrate. We have a secondary carbon here, right? This is a secondary alkyl bromide. So that means that we could be doing SN2 or E2. If it was tertiary, we would say no SN2 because the nucleophile would not be able to access that LUMO to do the backside attack. So we're not going to get SN2 on tertiary alkyl halides. You can rule it out. So if this were tertiary, we'd go done, E2. Instead, we have to look now at the temperature. And the temperature is hot. Now, remember, we talked about this for a while. I'm not going to go through the whole thing again because we talked about this for like 10 minutes last week. But because of the Gibbs free energy equation, something that is entropically favorable will become more favorable at higher temperatures. And elimination reactions are entropically favorable because you're going from a substrate and a base to the conjugate acid of the base, the elimination product, and the leaving group, right? So you're going from 2 things to 3 things. That's a dispersal of matter. So that's entropically favorable, which means a positive a positive delta S. And then if that temperature is very high, then the entropic favorability becomes magnified, right? This term becomes more and more positive, and we're subtracting it from the delta H, so it becomes more likely that delta G is negative. So entropically favorable processes become more likely to be spontaneous at higher temperatures, which translates in our situation to hot temperatures. If you're choosing between something like SN2 and E2, hot means favor E2. If we didn't know the temperature, we'd be scratching our heads. And in fact, we would, at ambient temperature, at room temperature, we'd probably get a mixture of elimination and substitution products. In reality, in the chemistry lab, you often get a mixture of products, right? You don't just all get only one thing. There'd be competing pathways. But here it's pretty hot. We might get a little substitution, but let's just say we're going to go all the way elimination. So we've got our hydroxide ion. Now, here's the thing. Which proton is it going to get? Because we need an alpha proton, and we have 3 alpha protons here on the methyl, and we have 2 alpha protons here on this internal carbon, on the secondary carbon. Now, that's where the sterics on the base matter. That's actually the 5th thing, is we want to look at the sterics of the base. And here we have a very sterically unhindered base. Hydroxide is tiny. So the activation energy associated with it approaching any proton on the molecule will be roughly similar. It's not going to have a very high activation energy for approaching the secondary proton over the primary. That means it's going to be a thermodynamically driven reaction, and it is going to prefer the most thermodynamically favorable product, the most stable product. And when we're forming an alkene product, that is going to be the most substituted alkene. So this hydroxide is going to get this proton, and it's going to go boom and boom and kick off the bromine there. And we are going to get this, the 2-butene. So that will be our elimination product. If we had a very bulky base like tert butoxide, then we would favor accessing the primary proton, because there would be a lower activation energy, substantially lower activation energy, with this big bulky base approaching this periphery, the side of the molecule, as opposed to the internal proton. And then we would get 1-butene as our elimination product. So that's a lot of stuff. But once again, strength of the base, hydroxide, we're ruling out SN1E1. We don't need to wait for a carbocation to form. It's going to go. It's going to do chemistry. Secondary substrate didn't tell us much. Heat told us to favor E2 over SN2. And then we looked at the sterics of the base to figure out which proton it was going to extract in order to tell us which alkene product was going to form. And we concluded the 2-butene, because this is more substituted, right? This is a di-substituted product, as opposed to it would be mono-substituted if we had 1-butene. More substituted alkenes are more stable for reasons basically of hyperconjugation, similar to why more substituted carbocations are more stable. So that's the first one. We went E2. Now let's do the next one. Let's take a look at this. We are going to have the same starting material here. And now let's go, right, SN1, SN2, E1, E2. So what do we have? Once again, the first thing that we're going to look at here is the strength of the base or nucleophile. So we have water. Water is weak. Water is very stable. Water is not like hydroxide. Hydroxide is the conjugate base of water. It is much, much more basic, much more strongly basic. Water is neutral. It's not especially basic, and is not really a great nucleophile because it is neutral, right? Things that have negative charges tend to be better nucleophiles. So if this is very weak, then it looks like we're going to have to wait for a carbocation to form, for something to happen. So let's get rid of SN2E2. Let me do that in red, just so it's very clear. We're not going to be able to do SN2 or E2. Water's not strong enough to push that substrate around. So let's let a carbocation form, then we'll decide. Okay. So leaving group leaves. With SN1 and E1, the first step is that the leaving group leaves. So here is our secondary carbocation. Now, and so with SN1 and E1, now the question is, now the base slash nucleophile will react, but is it going to coordinate to the plus charge, or is it going to grab a proton and do elimination? And here, once again, we're going to look at the temperature. The temperature is a bit colder now, right? 0 is pretty cold. Running this in a dry ice bath or something like that. And so if it's cold, for the precise same logic as we talked about a second ago, with hotter temperatures, something that's entropically favorable is going to be more likely to be spontaneous. Here, that's not really a factor, right? The entropic favorability is not as big of a factor because of how cold it is. Now enthalpy is more dictating what's going on. So we're going to prefer SN1. We're going to go SN1 here. And with SN1, that means water is going to attack. So let's say water attacks. And now here is something very important. We have to understand that when we do SN1 reactions, if we are forming a chiral center, we are going to get a racemic mixture. And so here is what we're looking at. Let's say we have water attacked that way, or we can have water attacking the other way. Now, the reason is this, and that has a positive charge as well. The reason is this. On the substrate, this carbon right here, that was an sp3 carbon that exhibits tetrahedral geometry. That's why we have the wedge and the dash bonds there. But the carbon that initially had 4 electron domains, 2 carbons, a bromine, and the implied hydrogen, one of those groups left, right? The bromine left with those electrons. So now that carbon has only 3 electron domains, which is why it is positively charged. But something with 3 electron domains is sp2 hybridized, right? And if it is sp2 hybridized, it is trigonal planar. So it's flat. The geometry around that carbon is flat. And if the geometry around that carbon is flat, if an incoming nucleophile is approaching, it can approach from either direction. And statistically speaking, if this is done trillions and quadrillions of times, you're going to get half this and half that. So the nucleophile is going to approach from either side, and you will get a 50-50. It's called a racemic mixture. We're going to get 50% of each stereoisomer. And then really quick, let's just get another water molecule to finish things off. We're just going to grab that proton. Oxygen, we'll grab one of these protons to neutralize the oxygen on the product. And so we've got 2 butanol, but we're going to have a racemate. We're going to get 50-50 R, 50-50 RS. So that is the R isomer. This is the S isomer, and we're going to get 50% of each. So with SN1, excuse me, still fighting this cold. With SN1, we have to be aware of any potential racemic mixture if we are generating a chiral center when the nucleophile attacks. Okay, moving on to the last one. One more time, we are going to react with R2 bromobutane. Let's get our little table here. If we are choosing between SN1, SN2, E1, E2, now we have tert-butanol. What is tert-butanol? Well, it is bulky, but more importantly, the strength, it is weak. It is approximately as weak as water, right? Because it is covalent. We have all covalent bonds. There are no ionic bonds here, right? The oxygen is covalently bound to that hydrogen. So it is neutral. It is as weak as water. So once again, we are going to get rid of SN2 and E2. And now we're going to look at some other stuff. We're going to look at temperature. So again, this is hot. Anytime it is hot, we're going to be favoring elimination. So we were choosing between SN1 and E1, and we're going to go E1. The other reason we're going to go E1 is because of the sterics of the base, right? We've got tert-butyl on the oxygen, very, very, very bulky. So that's unlikely to coordinate to anything. So let's go ahead and it's E1. So the first step of both the for SN1 and E1, the first step is the same. The leaving group leaves. So here's our carbocation. Now, here's the thing. We have, I'm just going to abbreviate this as T-butyl. We have our tert-butanol that we decided we're going to do elimination. Again, we have two different kinds of protons. There are 3 protons on the methyl. There are 2 protons on this CH2. And doing elimination with either of these sets of protons will yield 2 different products, just like up here with the first one, with the E2. Now, in this case, though, the tert-butyl group is so bulky that this is going to be kinetically driven rather than thermodynamically driven. Thermodynamically driven means going towards going towards the most stable product, which was the most substituted alkene product. Now, if it's kinetically driven because of sterics, because there's a difference with activation energy where that base is approaching, we're going to go with the one with the lowest activation energy. And the one with the lowest activation energy is going to get this terminal proton over here. And we're going to get that elimination product there to get 1 butene. So this is the less thermodynamically favorable product because it's going via the kinetic pathway, the kinetically favorable pathway, the lower activation energy. And again, that is because of the bulkiness on that base. That's what's driving that. So we did an E2, we did an SN1, and we did an E1. And that's a very good problem to help you, number one, go through that process of figuring out which mechanism we're going to use. And once again, the factors are in order, the way that I like to think of it. The first thing you're looking at is the strength of that base. Is it ionic? Is it strong? Is it neutral? Is it weak? And that is going to allow you to go towards SN2E2 if it's strong, or SN1E1 if it's weak. So right off the bat, we're narrowing it down by 50%. Then you're looking at the degree of substitution on the substrate. None of these were tertiary, but if any of them was a tertiary alkyl halide, you could rule out SN2. Not going to happen. Sterically, not possible. Then you look at, well, you can look at leaving group ability, although usually you're looking at stuff with pretty good leaving groups. Then you look at temperature. Temperature is telling you whether you're leaning towards elimination or substitution in general, though it doesn't tell you E2, E1, SN2, SN1, but it tells you elimination over substitution or vice versa. And then lastly, the sterics on the base or nucleophile. If it's very, very bulky, it will tend to go elimination. And not only that, but it will go, just to be clear, this is called the Hoffman product. So bulky bases favor Hoffman, not bulky, right? Unhindered bases prefer the Zaitsev elimination product. So that's good terminology to know. Zaitsev versus Hoffman. Zaitsev is the more substituted possible elimination product. Hoffman is the less substituted possible elimination product. So yeah, that's excellent practice for those. Let's see if I missed anything. Let me just go. So Max Cat asks, how do we differentiate between certain functional groups? Some of them are very similar and some are inside others. So that's a good question. There's really no, I mean, I would say flashcards, right? I think what you mean is that, like, say, for example, an amide is like a ketone and an amine put together, or an aldehyde and an amine stuck together. Yeah, that can get confusing. So really, we're just saying that you got to memorize them. Unfortunately, there's not that much memorization in organic chemistry, honestly. The only 2 things you have to memorize are all of the functional groups that you're responsible for, and then you do sometimes have to memorize, you have to be able to recognize certain sets of reaction conditions and go, oh, when I see that, I know I'm doing anti-Markovnikov hydration, whatever it is. So that is memorization, but that's about it. Spanish Prince, no, I will not cover acylation tonight. I'm going to stick with the SN1, SN2, E1, E2, and then I'm going to introduce addition reactions, and then we'll focus mainly on addition next time. MOA for Life asks about the difference of enantiomers and diastereomers. So we did talk about that last time. Let me see here. I will erase some of this. So enantiomers, okay, let's say we have, okay, here is a molecule with two chiral centers. The enantiomer is the mirror image, right? So if you want to get the enantiomer, you invert the stereochemistry at every chiral center. So here's a chiral center. We inverted it, went from the wedge to the dash. Here's the chiral center. We inverted it. We went from the dash to the wedge. These are enantiomers. The enantiomer is the mirror image. You can either literally draw the mirror image, or you can just invert every chiral center. So every molecule has every chiral molecule has one enantiomer. That's it. But a molecule can have many diastereomers, and a diastereomer is where you it is a stereoisomer that is not the enantiomer, meaning if you change one or more but not all of the chiral centers, you get a diastereomer. So for example, if we invert the bromo but not the hydroxyl, or if we invert the hydroxyl but not the bromo, right? Both wedge or both dash. These would be diastereomers. They are not the mirror image, but they are stereoisomers. It is a different stereoisomer. So a molecule with 6 chiral centers can have dozens of diastereomers, but any molecule will only have one enantiomer, the mirror image. So if you had a molecule with chiral centers R, 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 the enantiomer would be S, 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 S. That's it. Then you would have many diastereomers, R, R, S, S, R, R, S, S, R, S, 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 R, R, S, right? All of the other possible permutations would give you a diastereomer, but there's only one enantiomer where it is the precisely opposite stereochemistry. I hope that answers the question. Iham Krame, does poor leaving favor the Hoffman or Zaitsev? I don't think leaving group is really a factor, right? Because, for example, if you're looking at an E1 mechanism, the leaving group has already left before the base has even approached the molecule, right? So leaving group ability doesn't really factor in there. It's really sterics. It's an issue of sterics. Do you have a very bulky base that favors a kinetic pathway toward approaching the more sterically available proton, or do you have an unhindered base that's approaching the interior of the molecule and going the thermodynamic pathway? Okay. Draw the product of the following transformation. So we have this sodium methoxide. Now, on an exam, you may see this, right? So we have to see that and know that we mean ions, right? We have to know that. Now, let's go through the same logic. Do we have something strong or weak? Well, it's strong. So SN1, SN2 E1, E2, we're going to say no SN1, E1, right? Because it's strong, it's going to push the substrate around. Okay, so there's that. So now we're choosing between SN2 and E2. Now remember, we do want to look at the degree of substitution on the substrate. And so here we have a tertiary. This is a tertiary alkyl halide, and so SN2 is not possible. So we have to do E2. Now, where are we going to get the proton from to do E2? We have protons here, we have protons here, and we have protons here. These two directions are symmetrical, right? But we also have methyl protons. So if we have something that's very hindered, we're probably going to get the methyl protons. If we have something that's unhindered, we're going to go towards the interior of the molecule. Methoxide is pretty unhindered, right? It's not quite as unhindered as hydroxide. We just have that methyl group on there. It's still pretty unhindered. So we can get, there's two protons here and two protons here. Any of them will lead to the same product. So let's just go ahead and get this one. And we're going to get that bond there, and we're going to get that leaving group to leave there. And we are left with that. So notice that if you got a proton on the left and you got the double bond there, it's the same molecule, just flipped on the other side. Right. Same molecule. Okay. Okay, number 4, draw the product of the following transformation. So here we have another ionic compound. Once again, if you may see this, right? But we have to know, right? This could be a little confusing. What's going on? We've got potassium, we've got sulfur, we've got a phenyl group. The key is really when you see potassium or sodium or magnesium or calcium, right? Those metals in columns in groups 1 or 2, those are exclusively counter ions, right? They're not going to be coordinating to anything, right? Well, sometimes they can loosely coordinate to an anion, but that's not what we're talking about here. So this is going to be our classic SN2 nucleophile, right? When we have S minus, it's a great SN2 nucleophile because it's not particularly basic, right? The sulfide anion is much, much larger than the oxy anion, right? And the larger it is, the less basic it is because it's able to distribute that negative charge around a larger volume, so it's more stable. So S minus is not as likely to go and get a proton, but it is a localized negative charge that is going to be able to act as an SN2 nucleophile. And so let's go ahead and do this. So this one was E2. Here we are deciding SN2. And remember that SN2 involves inversion of stereochemistry. And so let's move on here. Okay, number 5. Which conditions will achieve the following transformation? So what did we do? What does it look like happened? So we definitely need to, here's the starting material, here's the product. And we want to identify what happened, right? What is the mechanism that happened? Well, we had a leaving group here. We had a bromo group there. We've got a double bond in the product. So it looks like an elimination, right? And so we could say E1, we could say E2. Let's try to force it to go E2, though. If you want to be sure that you get a particular product, E2 is going to ensure that there's no kind of funny business, no rearrangement or anything like that. So let's figure out how to force this to go E2. Now, which proton was used in the elimination? So let's go ahead. Let's call this CH2 and put another H there. So I'm just displaying one of these here to show what happened mechanistically. Clearly, a base got one of these protons on one of the methyl groups, either of the methyl groups, and got the double bond right there and kicked off that group there. So that's why we have a double bond here on this terminus instead of internal, right? It did not get one of the protons there and get that there. So this means this is a Hoffman product. So something did Hoffman elimination. So how can we ensure that we get Hoffman elimination? You want to bulk up that base, right? And so the classic E2 Hoffman promoter is going to be your tert butoxide. So CH3 COK, right? So that looks like this. Right, there's your tert butoxide. You've got a carbon with 3 methyls, and so this is a lot of steric hindrance, right? And so because it's so bulky, there's a lot more. It's a much higher activation energy associated with approaching one of these protons over there. So it's not going to do it. It's going to go Hoffman. It's going to be kinetically driven, and it'll get this proton here on the exterior of the molecule. It just kind of floats by the side, snags it, and then we get our elimination, kick off the bromo group, and there's our E2 Hoffman elimination product. Looks like one person got it there. Okay. All right, let's check out this one. Draw the product of the following transformation. So we have this tertiary alcohol. We have sulfuric acid, and to be clear, it is aqueous, right? We don't dump pure sulfuric acid in there. It's typically aqueous. And this little triangle means hot. This triangle means heat. Okay, so if you haven't seen that symbol before, that's what it is. So what are we going to do? Well, okay, we have a very strong acid. So if you have a very strong acid, that's a clear indicator that we're probably going to do an acid-base reaction if we have a base. If we can identify a base that can accept the proton via Bronsted-Lowry, where we're talking about proton transfer here, then we're probably going to get an acid-base reaction. So here is our H+, we write sulfuric acid, very strong acid, source of protons. What can accept a proton? Well, we've got a hydroxyl here. The oxygen on the hydroxyl certainly can accept a proton. So let's do that. So now we have H2O plus, couple of methyls, boom. Okay, so what does that do? Well, now we know that hydroxyl is a bad leaving group, but water is a good leaving group, right? Water is very stable by itself. If water leaves with the electrons in this oxygen-carbon bond, the oxygen will be neutralized and we'll just have a water molecule. So that's a very good leaving group, and we have a tertiary substrate. So that's actually going to work out just fine. And so let's let that leave. And now we have our tertiary carbocation, which is stable, right? As far as carbocations go, it's the more stable. That is a tertiary carbocation. Now, what else do we have? Right, we're not going to leave the carbocation. We know it's aqueous. So not only do we have the water moiety that just left to become a water molecule, but we also have other water molecules in solution. So what can a water molecule do? Well, it could coordinate to the carbocation, but it also could grab a proton and eliminate. And we are in strongly acidic conditions, so water certainly can pick up a proton to become hydronium. We've got tons of hydronium in solution already anyway, because it's an acidic solution, acidic conditions. But remember, it's hot. So it's hot. We're thinking maybe we're going to favor elimination over substitution. Now the question is, which proton are we going to get? So we have 3 protons there, 3 protons there. Actually, all 6 of those are chemically equivalent. And then we have 2 protons over here. So which proton are we going to go with? Water is very sterically unhindered, right? It has equal access to all of these protons. So it's going to go by the thermodynamically favorable route. We're going to go Zaitsev. We're going to get the proton on the interior. And we're going to put that pi bond there so we can neutralize the carbocation, get our alkene product. And so there is our E1D product. So it's E1, and then the D is for dehydration. So dehydration is we lost a water molecule, right? Losing water, dehydration. So it's E1D because it is E1, right? It's the same as if like a bromo group left. It's just that we started with a hydroxyl and protonated it. Water is a good leaving group, just like a bromo group is a good leaving group. So it is E1, right? Leaving group leaves, and then we got the proton and formed the pi bond. So it's E1, but we put the D in there because it's a dehydration. E1D. Okay. William Osuma, MCAT Orgo. So I have always found that my organic chem students do very well on the organic chem portion of the MCAT. So there's nothing super particular about MCAT Orgo. It is just kind of as far as I'm aware, I never took the MCAT, but it is a lot of just mechanisms and acid-base stuff and things that are a little bit more biochemistry oriented. So I don't think it's a ton about organometallics and things like that. Maybe not a lot of spectroscopy, but definitely biomolecules and trying to understand biomolecules and pKa and reactivity and things like that. Jalen GY asks, what does the E mean? The E means elimination. Right? An elimination reaction is where you have a leaving group and a proton. The leaving group and the proton are eliminated, and a pi bond is in their place between the two carbons that had those there. So E is for elimination. Rainy Cube asks, so what does the long multi-segmented tail represent? The long thing between CH3 and the junction of other things. So definitely the first thing we need to know to do any OChem whatsoever is understand the line notation. Every vertex and endpoint is a carbon atom. So that's a CH2, that's a CH2, that's a CH2, that's a CH2, right? These are carbon atoms, and the hydrogens are implied. Carbon, hydrogen, hydrogen. So this is sort of a time-saving thing, right? Organic molecules are carbon-based molecules. So we don't even write in the carbon. Actually, typically, we don't even write the CH3 right there. That's just there for this particular. You can, but you don't have to. That they are implied. But these hydrogens also, we must understand they are there. So we definitely have to look at molecules in line notation and know what's there. We have to know that all of these vertices are carbon atoms. We have to know that they are attached to hydrogen atoms that are not drawn, right? We're trying to save time. That's all it is. Raya NN asks, if there were only methyl protons, would the reaction still happen? Yes, absolutely. The reaction would still happen. There would be only one product, right? If you were doing E1 and you had this, you would get that, right? Basically, you would have 9. I can't do it. That looks horrible. You would have 9 chemically equivalent protons. So getting any of the protons would lead to that product. That's all it is. Okay. Let's move on to number 7. Okay, here's an interesting one. So draw the product of the following transformation. This is similar to the last one, at least at the beginning, but it's going to take a little bit of a turn here. So we've got sulfuric acid. We've got a source of protons. We've got a basic moiety here. The hydroxyl group can be protonated. So let's protonate. Okay, so again, we have a good leaving group here, but water's not really going to leave and generate a primary carbocation, right? A primary carbocation is not very stable. But look at what we have. We have a four-membered ring, and there's a lot of ring strain on that four-membered ring because it's forcing it to its torsional strain, right? There's angle because of it's forcing it to adopt 90-degree bond angles, whereas sp3 centers prefer to be 109.5. So this ring is kind of dying to break open. So look at what can happen here. We can have rearrangement of this ring. We can go like that. So this carbon-carbon bond will leave one of the carbons and attach to that carbon and kick off the water. And now all of a sudden, we have this. We have one, two. Yeah. Oh, no. Yeah, it's right here. Right. We now have a five-membered ring. And so this carbon right here lost a bond. So here's the new bond. Right? This is the new bond, right? So this carbon is this one, and that left that carbon and attacked this other one to kick off the water. And now we have a carbocation. Now we have a tertiary carbocation. So the leaving group was kicked off, but a lot of good things happened, right? Number one, we went from a four-membered ring to a five-membered ring, which is much more energetically favorable. And we got a tertiary carbocation instead of what would have been a primary carbocation. If water left, we're not going to get the primary, but we can get a tertiary, right? Now, what do we have? We are trying to finish this off. This is another E1D, right? And so we have water. And so is water going to get a proton over here, or is it going to get a proton over here? And so what we're asking is, again, about sterics, and water is very sterically unhindered. So we're going to be able to get this proton over here, and we're going to get the more favorable, the more thermodynamically favorable elimination product. If we had gotten protons from over here, that would have ended up exactly the same, just flipped on the other side. So those are equivalent. So this is another E1D, but we had a rearrangement. We had a ring opening here. So this is the key step where this carbon attacked that carbon, and that opened the ring up from 4 to 5. Crystal asks, but what happened to the SO4? So yeah, what happens with this, right? So here's sulfuric acid. If you put sulfuric acid in solution, in aqueous solution, it will immediately protonate water, and so you'll end up with O minus and H3O plus. So sulfuric acid is just donating the proton, typically to water, and then to make hydronium, and then hydronium is floating around that will protonate the substrate. It's obviously not impossible that sulfuric acid could directly protonate this hydroxyl group. Certainly that can happen. It's just that think of what's going on in solution, right? You have a lot of solvent and you have comparatively very little substrate and reactant. And so when you dump something in, if it can react with solvent, it'll react with solvent immediately because it's surrounded by solvent. So you dump in the sulfuric acid, you're going to protonate water molecules, get a bunch of hydronium. Then hydronium is floating around, and hydronium will in turn protonate the substrate. And so actually empty leave this, we probably will get very little sulfate in solution. We're going to remain bisulfate because this is not a particularly strong acid or nowhere near as much as sulfuric acid, of course. So probably get predominantly bisulfate in solution. Loco Hombre says, does E stand for elimination? Yes, E elimination, E1, and then D is dehydration. Very cool. Okay, we got time for one or two more here. So let's take a look at this. So we also, there are modifications that we can do with SN2. So OH is a bad leaving group, right? We know that we could protonate it. We can protonate it and get it to leave, and we can do SN1 or E1 that way. But when you have a carbocation intermediate, number one, you open yourself up to carbocation rearrangements, like the one we just saw. Number two, even if you don't rearrange, if you get a nucleophile approaching, that's an sp2 center, it's trigonal planar, you're going to get a racemic mixture, right? So what if we want stereospecific products? So we want to do SN2, but we want to do it on an alcohol. It's not going to work because we can't do SN2 on a hydroxyl. But if we use tosyl chloride, so tosyl chloride, we can tosylate this. And what that does is it turns it into a leaving group derivative. So we have O-tosyl. And tosyl is basically tosyl chloride is basically a large group with a phenyl ring, such that if O-tosyl leaves, that negative charge is now highly resonance stabilized. So long story short, the tosyl group makes this a good leaving group, right? So hydroxyl, bad leaving group, O-tosyl, good leaving group. So now we can do SN2. So KCN, we have this is a great classic SN2 nucleophile. Now that can go in and do SN2, and that's going to give us our product. And so here we had retention of stereochemistry because no chemistry happened at that bond. It was just that the oxygen attacks the tosyl chloride. It attacks a sulfur atom and then kicks off a chloride. And so now we do have our inversion of stereochemistry because we're doing SN2. So there is that there. And so this is if you want to do SN2 on a hydroxyl, you can use a leaving group derivative. So tosyl chloride, there's also mesyl chloride, trifle chloride. You're putting a tosyl group or a trifle group or a mesyl group. There's a few different ones on there. Now we have a good leaving group that is ready for SN2. So this is leaving group derivative followed by SN2. Okay, let's go ahead and do one more, maybe two. Yeah, we can probably get both of these. So, all right. 9. Which conditions will achieve the following transformation? So we're gone. We're finished with SN1. Maybe I'll do a little bit of SN1, SN2, E1, E2 next time. Maybe one problem or two problems. But now we did a lot of that. So let's move on to addition reactions. So the easiest, without giving it away, but there's one addition reaction that we tend to learn first because just in terms of the structures that you produce, it's very easy. And so the easiest addition reaction, the first one that we tend to learn is hydrogenation. And we can do hydrogenation over platinum metal or palladium metal. There's a lot of different ways to do it, but we can hydrogenate these pi bonds. And this is an example of organometallic catalysis. So if you have this metal surface, the substrate and the hydrogen can adsorb onto the metal surface. swim around on that. They can translocate on there, find each other, and then create carbon-hydrogen bonds in a way that's impossible without the metal surface. So this is actually an example of heterogeneous catalysis because it's happening between different phases. You have a solid metal support, and then whether in the gas phase or in the aqueous phase, or in the solution, can go up to the solid, adsorb, react, and then leave. And so the end result is that you lose pi bonds, right? Hydrogenation causes you to lose pi bonds. So the simplest one, hydrogenation over platinum metal, is a common surface to use. We just lose the pi bonds, and you go from the alkene to the alkane. That's all it is. So we're getting into addition reactions now. And so addition reactions are different from substitution or elimination, right? Substitution reactions exchange one substituent for another. Whether it's SN2, comes and kicks it out, or if it's SN1, it leaves and then the other one comes in a separate step. You're replacing a substituent with a different substituent. Elimination reactions, we're losing a leaving group and a proton and forming a pi bond. With addition reactions, pi bonds are the substrate, right? Alkenes, or also alkynes. Right now we're looking at alkenes. Alkenes are the substrates. They're the starting material for addition reaction. And for any addition reaction, we're adding two groups, one to each of the carbons participating in the pi bond. Here's the pi bond. We're going to lose the pi bond. We'll keep the sigma bond, lose the pi bond, a new group here, a new group here, one for each carbon. That is called an addition reaction. It's a very large class of reactions. We're going to look at all kinds of hydrohalogenations and dihalogenations and hydrations and many different kinds of addition reactions. But so hydrogenation is where we're adding a hydrogen to each atom, to each carbon from the pi bond. So here, there's not much more to say, right? We've lost the pi bonds. The hydrogens are implied, but they are here, right? We got the new hydrogens are here, and I'll just say CH2 in there, right? So these came from these, right? The molecular hydrogen added, and now we have more hydrogens on there, right? That's all that is. So that is hydrogenation. One more real quick because it's related. Which conditions will achieve the following transformation? So what does this look like? We have a bromine and it's gone. How are we going to just kick off the bromine? Well, do we have a way to get rid of leaving groups like that? Well, we could do elimination, right? So what if we did some elimination? And so what is the best way to ensure that we're going to get elimination? Well, we could do tert butoxide. That would be good, right? Let's do tert butoxide. Put the potassium counterion there. And so we could be getting either of these protons. It's probably going to go this way because it's a little more sterically available. But it actually doesn't really matter which one we get. And we'll see why in a second. So let's say we do that and we get our, here is our product. We've got the alkene there. And now, what did we just say? What did we just say we can do to get rid of pi bonds? We can just do some hydrogenation over, whoops, not 2 there. That's ridiculous. H2 over platinum metal, palladium, right? There's different supports you can use. This is the classic. Just memorize this. H2 over platinum. That's your standard hydrogenation where we're just anywhere there's pi bonds, we lose them. That's it. And these are not chiral centers, so we don't have to talk about stereochemistry. It is syn addition. So syn means the hydrogens come from the same side because they're stuck to the metal surface. Here's the metal surface. The hydrogens are sticking out like that, right? So the starting material coordinates to the to that, and then basically the hydrogens cannot add on opposite sides because they're stuck to the same solid surface. But we'll get more into syn and anti next time, as well as Markovnikov and anti-Markovnikov. And so that's it. We did E2, and then we did hydrogenation. Let me just see if I missed anything. I don't think I did. What would happen if not symmetric E or Z? Empty, leave this asks. So we didn't really care this time because I knew that we were going to do hydrogenation. So we're just going to lose the pi bond anyway. And so E is preferred energetically. In this case, it would have been E as drawn because we're already in that zigzag. And so we're forming that pi bond in a way such that E would probably predominate. But it didn't matter once again because we know that we're going to the alkane product. Last question. CLR spirit in a reaction with a strong base like methoxide. What conditions favor elimination, E2 over substitution, SN2, and how do sterics play a role? So if it is strong, if it is bulky, we're going to go E2. But if it is not bulky, we're not sure. That's where temperature comes in. If it's hot, we're going to favor E2. If it's cold, we're going to favor SN2. If a temperature is not given, you're going to get a mixture, right? And in fact, oftentimes you do get a mixture in the lab. It's not always so rigidly one thing and not the other. But so definitely sterically hindered bases will favor elimination. And then temperature will high temperatures favor elimination, low temperatures favor substitution. Okay, so that's it for this week. We just barely started scratching the surface on the addition reactions. So next week, we're going to do basically all addition reactions. Actually, yeah, definitely next week, we'll do all addition reactions, and then that'll spill over into the following week too, because they are that's a huge class of reactions that every OChem 1 student is going to be learning about. So stay tuned for next week. Once again, check out the QR code there for Chegg to see all of the various office hours they offer. Otherwise, I will see you next week, 5 p.m. Pacific, next Tuesday, the 25th,